In this week lecture, we are going to look at number systems and basic arithmetic. As you saw in the previous lecture, you noticed that numbers are essential to the operation of a computer. And in this week, we're going to take a closer look at them. So on this slide, we are seeing different number systems and different representations of number. So on the right, you can see your day-to-day number that you are using. You see the digit of 0 to 9. And you might recognize it in like different languages. There's the Roman number system, for example. The image on the bottom, you can see the tally system. So you have to use that probably for something that it's progressing, right? So a number that is changing and you're keeping track. Like, for example, a voting or a score of a game that is changing and you're doing this tally. The bigger picture that you see here, that is basically the Babylonian number system, and that has 59 like character or different symbols. So why am I showing you this? The main point here is that we have different representation for the same value of a number. So another concept that is important to know, which we already are familiar with, is the positional notation. So basically, in positional notation, same symbol could be used to show different orders of magnitude. So what does that mean? For example, this digit of 1, so that's a symbol. And depending on the location or the position that this digit is showing, it has different value. So if it's here, like in the first one, it's going to be 1. If it's going to be like on the second one, it's going to be 10, 100, and 1,000. So that's basically the idea of positional notation. So how do we calculate that? So first thing I should tell you is that, and you know probably, is that we are on a day-to-day basis, we are using the decimal system. So this number that you see here, 1,125, that is a decimal system, and the base is 10 in a decimal system. So that's why you see this radix that you see here, this 10, and that is showing the base. But because on a day-to-day basis we are always using this system, we don't put this one. So you add 1000 plus 100 plus 20 plus 5, and you're gonna get 1125. So that is trivial in the base 10. But let's say this base was different and you wanted to calculate it in your decimal system. The way that works, you see this example here. So when we have the 5, when I say the value of this is 5, what I'm actually doing is doing 5 times 10 to the power of 0. So any number to power of 0 is 1. And then I'm doing add 2 times 10 to power of 1. So basically I'm doing 2 times 10, and that's going to be 20. Then I'm doing 1 times 10 to power of 2. So that's 100, and so on. So basically you index these, so you put 0, 1, 2, 3, so on. And then the value of each position gonna be the base to the power of that index. Same number could have different representation, as we talked in the beginning of the lecture. So all of these numbers, that they're all equal. The value of each of them are 255, but they are in different bases. So in base 2, you're gonna have this one, and in base 16, you're gonna have FF. And also, it's like one side note to mention here is that you see, as we increase our base, actually the number is become smaller, so less digits. So compare base 2, which is 6, 7, 8 digits, versus base 16, that is only two digit. And our base 10 is going to be somewhere in here. So here we have the decimal numbers, and this is the number that we are using every day. we talked about this, the base is 10, and that is also known as radix. The digits are 0 to 9. So for every base, we have the number of that digit. So for example, base 10, we have 10 different digits. So example here, number 510, and this number here, that's the base, is just showing that we are talking about the decimal number. So if we are indexing that 0, 1, 2, and how do we calculate it is 5 times 10 to the power of 2 plus 1, we get this 1 from here, times 10 to the power of 1, and then 0 times 10 to the power of 0. Binary numbers exactly follow the same rule. So the difference is that the base is 2, we have 2 digits, and those are going to be 0 and 1. So that's the only 2 digits that you can use in binary system. They are so special, we name the digits. So each digit is called a bit. So that's 1 digit. It's called a bit, and that's actually a size in computing. Here we have example. So 1001 in base 2, we're gonna convert that to our decimal system. So what do we do first? We're gonna put the indexes, so from the right, and sorry for this spacing here, so this each is for one of them. So this is gonna be 0, 1, 2, 3. We just index them. And then the next thing to do is to calculate each value, basically the value of each position. So the first one gonna be 1 times 2 to the power of 3, and then 0 times 2 to the power of 2, 0 times 2 to the power of 1, and then 1 times 2 to the power of 0. So here it's basic math. All of them are times by 1, so that's basically out. So 2 to the 3, that's 8. 2 to the 2 is 4, but times 0, so that's 0. This is 2, but times 0 again, so that's 0. And then 1 times 1. So it's basically 8 plus 1, which is 9. So 1001 in binary is basically the number 9. So here we have a binary number, and we are trying to convert it to a decimal number. And this is just kind of a recap. We talked about this already. The way is to calculate the value of each position and then times by that digit. So how do we do that? We index from right to left, from 0 onward. The value gonna be the base to the power of that index, so 2 to the 7 times 1, we ignore the zeros, 2 to the 5 times 1, and 2 to the 4 times 1. So that's what we have here. And then we basically add them to get 176, and that's gonna be this binary number in decimal. So what about the other way around? So if you have a decimal number and you want to convert it to binary, so this is the opposite way. So for this, we have 2 different ways that we're gonna look into. The first way is to find the largest powers of 2 into that number. So what I mean by that is that, so our number is 211. If we look at our slide, so this one, the number was 211. So 211 fits somewhere between here, right? So what is the largest power of 2 that is smaller than our number? So that's going to be 128. So what we do here, we going to basically get 211, which is our number, and then find the largest power, so 128, and then subtract that. So this is going to be 11, 0, and then 11 minus 8 going to be 3. 0 we cannot do, so this is going to be 10, this is going to be 1. 10 minus 2, 8, and 0. So then we have 83. So what we had here was 2 to the 7, right? Because we got a 128. And then we have 83. So what is the largest number that we have? It's gonna be 64. The largest power of 2 that is smaller than this number. So then we minus this one, 64. This is gonna be 13 and 7. So 1 and 9. So 19. So we have to continue this. So what is the largest power of 2 that is smaller than this 19? We have 16. That's 2 to the 4. So 19 minus 16 gonna be 3. And then again, we have to continue. What is the largest power of 2 that is smaller than 3? That's gonna be 2 itself. Then we get 1. And then we get 2 to the 0, which is 1. So we have another one and we get 0. So we have to go all the way to get 0. And if you look at our numbers, let me try to change the color. So this was 128 was 2 to the 7. 64 was 2 to the 6. 16 was 2 to the 4. 2 was 2 to the 1. And 1 here was 2 to the 0. So you can see here that basically we broke these 211 into powers of 2. And you have to start from the largest. So that's the only trick here. And if you add all of these, obviously we're going to end up with 2 to the 2 to 211 because we just kept subtracting them, right? So then the next step is easy because if we have these sums and if you are looking at the binary representation, if we index these, so this was here 0, 1, 2, 3, 4, 5, 6, and 7. So if you look, whenever we have a power, it's gonna be a 1 because we have 2 to the 7. We have 2 to the 6. We don't have 5. We have 2 to the 4, 2 to the 1, and 2 to the 0. So basically, it's the other way of this. It's the opposite of this other way. And that's one way of converting decimal number to binary. So here we have the second way of converting a decimal number to a binary number. This is done by divisions, and we call it the divisions method. So if you are dividing your number by 2, you're gonna find basically the power of 2 that are in the number. Here we have the number 222, and we want to convert that to binary. So what we do, we start by dividing that by 2, and it works with all the bases, by the way. So if you are going base 8 or 16, we can still use the same method. So basically you divide by your base. So when you divide 222 by 2, you're gonna get 111, and there will be no remainder. So this is something that basically is kind of like the first division that you learned. So if it was, for example, number 7, just as a side example, and then you're dividing that by 2, you would get you get 3 for the quotient. So that means we don't want like decimals here. So you want only the whole number. So that would be 6, and then you have the remainder of 1. So that would be your 7. So always we are going with the whole number. And basically we continue doing this. So first you divide by 2 your number, you get 111 and no remainder. Then you get this number here, which is your quotient, and you take it to the next level. So then you have 111, divide by 2, you are getting 55, and the remainder is 1. So you have to do the again the old school. So 111 divide by 2, you start from here, so you have 5, that's 10. And you can do it in a different way if that's how like you learn. 11 divided by 10, sorry, 11 minus by 10 is 1. We drop the 1, and then another 5, that is 2 times 5, 10, and you get 1 as a reminder. So that's your quotient here, and this is your reminder. So 51 and 1. And then we again take this 51, 55 to the next level, and then you continue that. So we keep doing this until we get 0 here on your quotient. So this is very important. I've seen students do a mistake that they stop this process when they get the 0 on the reminder. I've seen that many times that happens. You have to continue dividing by 2 until you get the 0 on the quotient. And then you may have a remainder. So once you get remainder 0 or 1 here, like that doesn't matter. You have to continue unless this one is 0, because then if it's 0, then you cannot divide more, like 0 divided by 2. You cannot do that. And after that, when you got that, you have your bit order from basically down to up. So if you write your number 1 1 0 1 1 1 1 0, and that's basically your number that you have here. And there is a convention for, to make it easier, we do every 4 digit. So we group them basically by every 4 digit, and we start from the right side. So basically this 4 and then this 4. So if this was like there was this one was missing here, like let's say we got the 0 here, you would have see that, okay, these 4 gonna be together, and then there is 3, so I probably need a 0. So I would write something like 0 1 0 1 1 1 1 0.